So here's something worth sitting with for a moment. Right now, as you're lying there, settling in, maybe pulling the covers up a little, your body is doing something extraordinary. Every atom in you, every single one, was forged inside a star that died before our sun was even born. The calcium in your bones, the iron in your blood, the oxygen you're breathing in right now, all of it was cooked up in a furnace millions of degrees hot, billions of years ago, in a star you'll never know the name of, because it exploded itself into oblivion long before anything on Earth was alive to name it. And somehow, across all that time and all that emptiness, those atoms found their way into you, into this moment, into a person lying in the dark, listening to someone talk about the universe. That's not poetry. I mean, it is poetry, but it's also just physics. And tonight, we're going to walk through it, slowly, gently, one piece at a time. All the confusing, beautiful, head-scratching things about how the universe works, why the sky is dark at night, what space actually is, how time can speed up and slow down, why gravity isn't really a force, what happened at the very beginning, and what might happen at the very end. We'll get to all of it, and none of it's going to feel rushed. If you drift off somewhere along the way, that's perfectly fine. That's kind of the point. The universe will still be here when you wake up. Let's start at the beginning. And I mean the very beginning, because that's where the confusion starts for most people. The Big Bang. You've heard of it. Everyone's heard of it. But here's the thing. Almost everyone pictures it wrong. When someone says Big Bang, you probably imagine a massive explosion happening somewhere in empty space, like a cosmic firework going off in the middle of a dark room, and everything flying outward from that one point. That's the image most of us carry around, and it's completely understandable, but it's not quite right. Here's what actually happened, as far as we can tell. About 13.8 billion years ago. And that number is remarkably precise. By the way, we've nailed it down to within about 40 million years, which sounds like a lot, but is less than 1/3%. The entire observable universe was compressed into a region smaller than an atom. Not just all the matter and energy, but space itself. That's the part that trips people up. It wasn't an explosion happening inside space. It was space itself expanding. There was no outside for it to expand into. There was no dark, empty room waiting to be filled. The room itself was being created as it went. Think of it this way. Imagine the surface of a balloon before it's inflated. Now imagine you're an ant living on that surface. As the balloon inflates, everything around you stretches. Every other ant on the balloon is moving away from you. But you're not moving across the surface. The surface itself is growing. There's no center of the expansion on the surface of the balloon. Every point on the surface is equally valid as a center. That's roughly what's happening with the universe, except instead of a two-dimensional surface, it's three-dimensional space. Every point in the universe is the center of its own observable universe. You, right now, lying in bed, are at the exact center of the observable universe. So am I. So is a random rock on Mars. That sounds impossible, but it works because the universe doesn't have an edge or a center in the way we normally think about those things. Now, the person who first figured out that the universe was expanding wasn't Albert Einstein, even though you might expect it to be. Einstein actually got this one wrong, which is a wonderful thing to know about him. When Einstein developed his general theory of relativity in 1915, his equations told him something he didn't want to hear. The universe couldn't be static. It had to be either expanding or contracting. And Einstein, brilliant as he was, thought that couldn't be right. Everyone in 1915 assumed the universe was eternal and unchanging. That was the default assumption. The stars had always been there, the cosmos was fixed, and that was that. So Einstein did something he later called the biggest blunder of his career. He added a fudge factor to his equations, a term called the cosmological constant, specifically to force the universe to stand still. He tweaked his own masterpiece because he couldn't believe what it was telling him. And then along came a man named Georges Lemaitre. Now, Lemaitre is one of those figures in science who deserves to be a household name, but somehow isn't. He was a Belgian priest, a Catholic priest, which is a detail that surprises a lot of people. And he was also a physicist and astronomer. In 1927, Lemaitre looked at Einstein's equations without the fudge factor and said essentially, what if the equations are right? What if the universe really is expanding? He published a paper proposing exactly that, and he went further. He reasoned that if you run the expansion backward, like rewinding a film, everything gets closer and closer together, denser and denser, hotter and hotter, until you reach a moment when the entire universe was concentrated in what he called the primeval atom, a single, unimaginably dense point from which everything began. This was a radical idea, and almost nobody paid attention to it at first. Lemaitre published his paper in a relatively obscure Belgian journal, and it was written in French, so most of the English-speaking scientific world didn't even read it. Einstein himself met Lemaitre at a conference and reportedly told him, "Your calculations are correct, but your physics is abominable," which is a devastating thing to hear from Einstein, but also, in hindsight, hilariously wrong. The observational evidence came from Edwin Hubble, working at the Mount Wilson Observatory in California. Hubble had access to what was then the most powerful telescope in the world, the 100-inch Hooker telescope, perched up in the San Gabriel Mountains above Los Angeles. And in 1929, Hubble published findings that changed everything. He'd been measuring the light from distant galaxies, and he noticed something remarkable. The light from nearly every galaxy he observed was shifted toward the red end of the spectrum. Red-shifted. And the farther away a galaxy was, the more its light was redshifted. Now, let's talk about what redshift actually means, because it's one of those concepts that sounds technical, but is actually beautifully intuitive once you hear the analogy. You know how when an ambulance is coming towards you, the siren sounds higher pitched, and then as it passes and moves away, the pitch drops? That's the Doppler effect. The sound waves get compressed as the source moves toward you, shorter wavelength, higher pitch, and stretched out as it moves away. Longer wavelength, lower pitch. Light does the same thing. When a light source is moving away from you, its light waves get stretched out, and stretched out light waves look redder. When it's moving toward you, the waves get compressed, and the light looks bluer. So when Hubble saw that distant galaxies were redshifted, what he was seeing was that they were moving away from us. And the farther away they were, the faster they were receding. This is Hubble's law, and it's one of the most important discoveries in the history of science. It means the universe is expanding, just like Lemaitre had predicted. Everything is moving away from everything else. Not because galaxies are flying through space like shrapnel from an explosion, but because space itself is stretching. The fabric of the cosmos is getting bigger, carrying the galaxies along with it like raisins in a loaf of bread that's rising in the oven. The raisins aren't crawling through the dough. The dough itself is expanding, and the raisins just go along for the ride. When Einstein saw Hubble's data, he finally accepted what his own equations had been trying to tell him all along. He dropped the cosmological constant and acknowledged that the universe was expanding. And he gave Lemaitre the credit he deserved. Years later, Einstein reportedly called the cosmological constant his greatest mistake. Although, and here's a delicious twist, decades later, in the late 1990s, astronomers discovered that the expansion of the universe is actually accelerating. And the best explanation we have for that acceleration looks an awful lot like Einstein's cosmological constant. So his biggest blunder might have been accidentally right, just for the wrong reasons. The universe has a sense of humor like that. But let's go back to the very beginning for a moment. Because the Big Bang itself is stranger than most people realize. When we say the universe was compressed into a point 13.8 billion years ago, we're not talking about a point sitting somewhere in space. We're talking about a state where our current understanding of physics breaks down completely. The temperatures were so high, the densities so extreme, that the laws of physics as we know them simply stop working. We can trace the history of the universe back to about 1/1,000,000,000 of a trillionth of a trillionth of a second after the Big Bang. That's 10 to the negative 43 seconds, a number so small it's basically meaningless to the human brain. But we can't go further back than that. Not because we're not smart enough, but because our best theories of physics, general relativity and quantum mechanics, contradict each other at that scale. We'd need a theory of quantum gravity to go further, and we don't have one yet. So the actual moment of the Big Bang, the very first instant, remains a mystery. It's the ultimate unanswered question. What we can describe, though, is what happened in the moments just after. And it's one of the most astonishing stories in all of science. In the first few minutes, literally the first 3 minutes, the universe went from an incomprehensibly hot, dense soup of energy to something recognizable. Within the first second, the fundamental forces of nature separated out from what may have been a single unified force. Quarks combined into protons and neutrons. Within about 3 minutes, those protons and neutrons started fusing together to form the nuclei of the lightest elements, hydrogen, helium, and tiny traces of lithium. This process is called Big Bang nucleosynthesis, and it's one of the strongest pieces of evidence we have that the Big Bang actually happened, because we can predict exactly how much hydrogen and helium should have been produced. And when we look out at the universe, the proportions match almost perfectly. About 75% hydrogen, about 25% helium, and just a whisper of lithium. The universe was writing its own recipe in those first few minutes. But here's what's fascinating, and this is something worth sitting with. For the first 380,000 years after the Big Bang, the universe was completely opaque. You couldn't see through it. It was so hot and so dense that photons, particles of light, couldn't travel any meaningful distance without smashing into a free electron and getting scattered in a random direction. It was like trying to see through the thickest fog you can imagine, except the fog was made of plasma, and it was millions of degrees hot. Light existed, but it couldn't go anywhere. The universe was bright, but blind. And then, around 380,000 years after the Big Bang, something beautiful happened. The universe had been expanding and cooling all that time, and it finally cooled enough to about 3,000 degrees Kelvin for electrons to be captured by atomic nuclei. Hydrogen atoms formed, helium atoms formed, and suddenly, for the first time, there were no more free electrons bouncing around to scatter the photons. The fog cleared. Light was free to travel across the universe, unimpeded. This moment is called recombination, which is a slightly misleading name because the electrons and nuclei had never been combined before. They were combining for the first time. But the name stuck. And here's the truly wild part. That light, those photons that were released 380,000 years after the Big Bang, when the fog finally cleared, they're still traveling. They've been traveling for 13.8 billion years, stretched out by the expansion of the universe from visible light all the way down to microwave radiation. And we can detect them. We can see them right now, today, with the right instruments. It's called the cosmic microwave background radiation, and it fills every corner of the sky. It's the oldest light in the universe. When you look at a map of the cosmic microwave background, you're looking at a baby picture of the cosmos, taken when it was just 380,000 years old. And it's almost perfectly uniform, almost the same temperature in every direction, but with tiny, tiny fluctuations, variations of about 1 part in 100,000. Those fluctuations are the seeds of everything. Every galaxy, every star, every planet, every person listening to this right now, all of it grew from those minuscule ripples in the cosmic microwave background. The story of how those tiny ripples became galaxies and stars, and eventually you and me, that's a story about gravity and about time, and about the strange behavior of matter on scales both unimaginably large and unimaginably small. And gravity, it turns out, is far stranger than you probably think. Most of us learn about gravity as a force, the thing that pulls the apple toward the ground, the thing that keeps the moon in orbit. Newton described it that way, and for most everyday purposes, that description works beautifully. But Einstein showed us something deeper, something that changes the way you think about the universe once you really let it sink in. Einstein showed us that gravity isn't a force at all. It's geometry. It's the shape of space and time themselves, curved and warped by the presence of mass and energy. And I know that sounds abstract, so let's slow down and really sit with it for a moment. Picture a trampoline, a big one, stretched tight and flat. Now place a bowling ball in the center. The fabric sags, right? It curves downward around the bowling ball, creating a kind of dimple, a well. Now roll a marble across that trampoline. If you roll it in a straight line far from the bowling ball, it barely notices the dip. But if you roll it closer, the marble curves. It follows the contour of the stretched fabric, bending its path toward the bowling ball. And if you roll it just right, with just the right speed and angle, the marble will actually orbit the bowling ball, circling around and around in that curved depression. That's the analogy people usually use for general relativity, and it's not perfect. No analogy ever is, but it captures something essential. In Einstein's picture, massive objects like stars and planets don't reach out and grab things with some invisible force. Instead, they warp the fabric of space-time around them, and other objects simply follow the curved paths that result. The Earth doesn't orbit the Sun because the Sun is pulling on it. The Earth orbits the Sun because the Sun's mass has curved space-time in its vicinity, and the Earth is following the straightest possible path through that curved geometry. In the language of general relativity, that straightest possible path is called a geodesic. And here's the beautiful thing. The Earth thinks it's going in a straight line. From its own perspective, it's just coasting through space, following the natural contour of the landscape. It's the landscape itself that's curved. Now, Einstein didn't arrive at this idea overnight. It took him about 10 years. 10 years of grinding, difficult, sometimes agonizing work. He published special relativity in 1905. That's the theory that gives us E equals mc squared, that tells us the speed of light is constant, that time slows down when you move fast. Special relativity was a revolution, but it had a limitation. It only dealt with objects moving at constant velocities in the absence of gravity. Einstein knew he needed to extend the theory to include acceleration and gravitation, and he had a crucial insight early on that pointed the way. He called it the happiest thought of his life. Here's what it was. Imagine you're standing in an elevator, a closed box, no windows. You feel your feet pressing against the floor. You feel your weight. Now, is the elevator sitting still on the surface of the earth, with gravity pulling you down? Or is the elevator out in deep space, far from any planet, but accelerating upward, being pushed by a rocket engine? Einstein realized that from inside the box, you cannot tell the difference. The experience of standing in a gravitational field is identical to the experience of being accelerated. This is the equivalence principle, and it became the foundation stone of general relativity. Think about what that means. If gravity and acceleration are indistinguishable, then gravity isn't some special, separate force. It's intimately connected to the geometry of motion, to the way objects move through space and time. And from that seed, Einstein spent the better part of a decade developing the mathematics to describe exactly how mass and energy curve space-time, and how that curvature dictates the motion of everything within it. He needed mathematical tools that didn't even exist in physics at the time. He had to learn an entire branch of mathematics called tensor calculus, largely with the help of his friend Marcel Grossmann, a mathematician who'd been his classmate in Zurich. There were false starts, wrong turns, months of frustration. At one point, in 1912, Einstein wrote to a colleague that he had never worked so hard in his life, and that compared to this problem, special relativity had been child's play. But in November 1915, he finally got it. He presented the field equations of general relativity to the Prussian Academy of Sciences in Berlin in a series of 4 lectures over the course of the month. The equations are compact, deceptively so, but they encode an extraordinary amount of information. They tell you that the curvature of space-time at any point is determined by the distribution of mass and energy at that point. Matter tells space-time how to curve, and curved space-time tells matter how to move. That's the whole thing, in one sentence. The physicist John Archibald Wheeler said it that way, and it's never been improved upon. And immediately, general relativity made a prediction that Newtonian gravity couldn't. For decades, astronomers had known that the orbit of Mercury was slightly off. Mercury's orbit isn't a perfect ellipse. The ellipse itself rotates over time, a phenomenon called the precession of the perihelion. Newtonian gravity could account for most of this precession by considering the gravitational influence of the other planets, but there was a leftover, a tiny discrepancy of about 43 arcseconds per century that nobody could explain. Some astronomers had even proposed the existence of an unseen planet, which they called Vulcan, orbiting closer to the Sun than Mercury, tugging on it. But Vulcan was never found, because it didn't exist. When Einstein plugged Mercury's orbit into his new equations, the answer came out exactly right. 43 arcseconds per century, on the nose. He later said that when he saw that result, his heart literally palpitated. He knew the theory was correct. But the confirmation that really made the world pay attention came in 1919, and it involved a total solar eclipse. General relativity predicts that light itself should follow curved paths through warped space-time. A beam of light passing near a massive object like the sun should bend, deflected by the curvature the sun creates. Newton's theory also predicted some bending of light, if you treat light as particles with mass. But Einstein's theory predicted exactly twice as much. So here was a testable difference. And the British astronomer Arthur Eddington organized 2 expeditions to observe the solar eclipse of May 29, 1919. One to the island of Principe off the west coast of Africa, and one to Sobral in northern Brazil. During the eclipse, when the moon blocked the sun's glare, they could photograph stars that appeared near the sun's edge and measure whether their apparent positions had shifted compared to where those stars normally appeared in the night sky. The results, announced in November 1919, confirmed Einstein's prediction. The light from distant stars was bending by the amount general relativity said it should. The headlines were extraordinary. The London Times declared, "Revolution in science, new theory of the universe, Newtonian ideas overthrown." Overnight, Einstein became the most famous scientist in the world. And it's worth pausing to appreciate what had just happened. A theoretical physicist, working with pencil and paper, had reimagined the fundamental nature of space and time, predicted a measurable effect that disagreed with the prevailing theory, and been proven right by observation. That's science at its most powerful. Now, here's where things get really interesting for our story about the universe. Remember those field equations, the ones Einstein presented in 1915? When you apply them not to a single planet or star, but to the universe as a whole, something unexpected happens. The equations don't want to sit still. They naturally describe a universe that's either expanding or contracting. And we talked about this earlier, how Einstein was so uncomfortable with that implication that he added his cosmological constant, that fudge factor, to hold the universe static, and how Lemaitre and Hubble showed that the universe really is expanding, and Einstein dropped the constant. But the deeper point is this: general relativity is the language of cosmology. It's the framework that lets us describe the large-scale structure and evolution of the universe. Without it, the Big Bang isn't a theory. It's just a vague idea. With general relativity, you can write down precise equations that tell you how the universe expands, how fast, and how that expansion changes over time, depending on what the universe is filled with. And what the universe is filled with, that turns out to be one of the most surprising and humbling discoveries in all of science. Because here's the thing, all the stuff you can see, stars, galaxies, gas clouds, planets, people, everything that emits or absorbs light, all of that makes up roughly 5% of the total energy content of the universe. 5%. The rest is invisible. About 27% is something called dark matter, and about 68% is something called dark energy. And if those names sound mysterious, that's because they are. We call them dark, not because they're literally dark in color, but because they don't interact with light. They're invisible to our telescopes. We know they're there because of their effects, but we don't know what they are. Not really. Not yet. Let's start with dark matter, because its story is one of the great detective tales of 20th century science, and it begins with a cantankerous, brilliant Swiss-American astronomer named Fritz Zwicky. In 1933, Zwicky was studying the Coma Cluster, a massive collection of over 1,000 galaxies about 320 million light-years away. He measured how fast the individual galaxies within the cluster were moving, their velocities, and then he calculated how much mass the cluster would need to contain in order to gravitationally hold itself together, to keep those galaxies from flying apart. And the number he got was enormous. far more mass than he could account for by adding up all the visible galaxies. The galaxies were moving so fast that the visible matter alone couldn't possibly generate enough gravitational pull to keep the cluster bound. Something else had to be there, something massive but invisible. He called it Dunkle Materie, dark matter in German. And here's what's a little heartbreaking about this story. Nobody really listened. Zwicky was right, but he was also abrasive, combative, and difficult to work with. He called his colleagues at Caltech spherical bastards. Bastards no matter which direction you looked at them. He made enemies easily. And his dark matter idea was so radical, so far ahead of its time, that it was largely ignored for nearly 4 decades. It sat there, this extraordinary insight, gathering dust while the rest of astronomy moved on to other things. It wasn't until the 1970s that the case for dark matter became impossible to ignore, and the person who made it impossible was an astronomer named Vera Rubin. Rubin had faced obstacles her entire career. She was told as a young woman that Princeton didn't accept women into its astronomy program. She was discouraged from pursuing research. She was underestimated at every turn. But she was persistent and meticulous. And she chose to study something that most astronomers considered boring: the rotation curves of spiral galaxies. She wanted to measure how fast stars at different distances from the center of a galaxy were orbiting. And what she found, working with the instrument maker Kent Ford, was something that didn't make any sense under the prevailing understanding of gravity and matter. She measured the orbital speeds of stars in the Andromeda Galaxy and in dozens of other spiral galaxies, and what she expected to find was a pattern that looked a lot like our solar system. Think about it this way. In our solar system, Mercury, the planet closest to the Sun, orbits the fastest. It whips around at about 47 kilometers per second. Earth, farther out, moves at about 30. Jupiter, way out there, lumbers along at 13. Neptune, at the edge, crawls at just over 5. The reason is straightforward. The Sun contains the overwhelming majority of the solar system's mass, so the closer you are to it, the stronger the gravitational pull, and the faster you need to move to stay in orbit. As you get farther away, gravity weakens, and orbital speeds drop off. This is basically Kepler's third law in action, and it's been understood since the 1600s. So when Rubin pointed her instruments at spiral galaxies, the expectation was that stars near the center, where most of the visible mass is concentrated in that bright glowing core, would orbit quickly, and stars out at the edges, way out in the dim outskirts of the galaxy, would orbit much more slowly. The light falls off, the mass should fall off, and the speeds should fall off. That's what the math predicted. That's what everyone assumed she'd find. But that's not what she found. Not even close. What Rubin and Ford discovered was that the rotation curves were flat. The stars at the outer edges of galaxies were moving just as fast as the stars much closer to the center. In some cases, they were moving even faster. And this was true not for one galaxy, not for a handful, but for every single spiral galaxy they measured. Galaxy after galaxy after galaxy. Flat rotation curves, every time. The pattern was unmistakable. Now think about what that means. If the stars at the edges are moving that fast, and the only mass holding them in orbit is the visible matter you can see, the stars, the gas, the dust, then those outer stars should be flying off into intergalactic space. They're moving too fast for the visible gravity to hold them. It's like watching a merry-go-round spinning so fast that the kids on the outer edge should be flung off, but somehow they're not. Something is holding them on. Something you can't see. Rubin was careful. She was rigorous. She published her results in 1980, and this time, unlike Zwicky's lonely proclamation in the 1930s, The astronomical community couldn't look away. The data was too clean, too consistent, too overwhelming, and Rubin herself was measured and precise in her conclusions. She didn't claim to know what the invisible mass was. She simply pointed out that the observations demanded far more matter than anyone could see, and that this matter had to extend well beyond the visible edges of galaxies, forming enormous invisible halos that dwarfed the luminous disks we see in telescope images. And here's the thing that really gets me about Rubin's story. She knew she was standing on Zwicky's shoulders. She was generous about crediting his earlier work, even though he'd been difficult and largely forgotten. She understood that science sometimes needs the same discovery to be made twice. Once by someone ahead of their time, and once by someone with the data and the temperament to make people listen. Zwicky had the idea. Rubin had the proof. So by the early 1980s, the astronomical community had to accept something deeply unsettling. Most of the matter in the universe is invisible. It doesn't emit light. It doesn't absorb light. It doesn't interact with light at all. It's not dark in the sense of being dim. It's dark in the sense of being completely transparent to every form of electromagnetic radiation we know how to detect. It interacts with gravity, and as far as we can tell, that's about it. It passes through ordinary matter, like ordinary matter isn't even there. Right now, as you're lying there, dark matter particles are almost certainly streaming through your body, through the earth beneath you, through everything, and neither you nor they notice. And we still don't know what it is. That's the honest truth. We've been looking for dark matter particles since the 1980s, and despite extraordinarily sensitive detectors buried deep in mines to shield them from cosmic rays, despite particle colliders smashing protons together at nearly the speed of light, despite decades of theoretical work proposing candidates like WIMPs, weakly interacting massive particles, and axions, we haven't directly detected a single dark matter particle. We know it's there because of what it does to the things we can see. We can map it. We can measure its gravitational effects with exquisite precision. We can see how it bends light from distant galaxies through gravitational lensing, creating those beautiful arcs and rings that Hubble Space Telescope images have captured. But what it actually is, what it's made of, that remains one of the deepest open questions in all of physics. Let's sit with that for a moment, because it's genuinely humbling. We've built a model of the universe that works extraordinarily well. We can predict the cosmic microwave background's temperature fluctuations to astonishing accuracy. We can trace the formation of galaxies, the distribution of large-scale structure, the abundances of light elements forged in the first few minutes after the Big Bang. And yet, roughly 27% of the universe's total energy content is made of something we cannot identify. We know more about what dark matter isn't than what it is. It isn't ordinary atoms. It isn't neutrinos, at least not mostly. It isn't black holes, though that was a serious hypothesis for a while. It's something else, something new, something that doesn't fit into the standard model of particle physics as we currently understand it. And then there's the other mystery, the even stranger one, the one that makes dark matter look almost cozy by comparison. Dark energy. Remember how we talked about Einstein's cosmological constant, that fudge factor he added to his equations to keep the universe static, the one he later called his greatest blunder? Well, the universe has a sense of irony, because it turns out something very much like the cosmological constant is real. It's just doing the opposite of what Einstein intended. Here's how we found out. In the late 1990s, two independent teams of astronomers were trying to measure the rate at which the universe's expansion was slowing down. Because that's what everyone expected. The universe is expanding, Hubble showed us that in 1929, and it's full of matter, and matter has gravity, and gravity pulls things together. So the expansion should be decelerating, like a ball thrown upward that gradually slows as Earth's gravity tugs it back. The only question was how fast the deceleration was happening, because that would tell you the ultimate fate of the universe. Enough matter, and the expansion eventually stops and reverses. The big crunch. Not enough, and the expansion continues forever, but keeps slowing down, asymptotically approaching some final coasting speed. The two teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were using a particular kind of stellar explosion called a Type 1a supernova as cosmic distance markers. These are beautiful objects for cosmology because they all explode with roughly the same intrinsic brightness. They're what astronomers call standard candles. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate how far away it is. It's the same principle as seeing a streetlight in the distance. If you know all streetlights are the same wattage, a dimmer one must be farther away. So both teams were measuring distant Type 1a supernovae, comparing their apparent brightness to their redshift, how much their light had been stretched by the expansion of space, and using that to map the expansion history of the universe. And in 1998, both teams announced results that stunned the physics community. The distant supernova were dimmer than expected. Not brighter, not right on target, but dimmer. Farther away than they should have been if the expansion were slowing down. The expansion of the universe wasn't decelerating at all. It was accelerating. Let that sink in for a second. The universe isn't just getting bigger. It's getting bigger, faster, and faster. Whatever is driving this acceleration is working against gravity on the largest scales, pushing space apart with increasing vigor. And nobody expected it. Nobody had a mechanism for it. It was, and in many ways still is, completely baffling. The 1998 discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011, and it fundamentally reshaped our picture of the cosmos. That mysterious accelerating force got a name: dark energy. And when cosmologists tallied up the energy budget of the universe, they found that dark energy accounts for roughly 68% of everything. Think about that. More than 2/3 of the universe's total energy content is this thing we barely understand at all. We don't know what it is. We don't know why it has the value it has. We don't know if it's truly constant or if it's changing over time. Some models suggest it could be a property of space itself, that empty space has an intrinsic energy density, and as space expands, you get more space, which means more dark energy, which drives more expansion, which creates more space. It's a kind of cosmic positive feedback loop that, if it continues, means the universe will expand forever, and eventually galaxies beyond our local group will recede so fast that their light will never reach us. The observable universe will shrink from our perspective until the night sky is truly, profoundly empty. But that's trillions of years from now. For tonight, what matters is this strange accounting. You, me, the Earth, the Sun, every star you've ever seen, every galaxy Hubble ever photographed. All of that is roughly 5% of the universe. Just 5%. The rest is dark matter and dark energy. And we're still working on figuring out what either of them actually is. There's something almost poetic about that if you let yourself sit with it. We've learned so much. We've mapped the cosmic microwave background with satellite missions like COBE and WMAP and Planck, measuring temperature variations of a few millionths of a degree across the sky. We've traced the evolution of the universe from a fraction of a second after the Big Bang to the present day. And yet, the overwhelming majority of what exists remains mysterious to us. It's not that we're ignorant. It's that every answer opens up deeper questions, and the universe keeps turning out to be stranger and more layered than anyone guessed. Which brings us to something that connects all of this: the question of how structure formed in the first place. Because the universe, right after recombination, when the cosmic microwave background was released, was almost perfectly smooth. Almost, but not quite. Those tiny fluctuations, those minuscule variations in density that we see imprinted in the microwave background, they're the seeds of everything. Every galaxy, every cluster of galaxies, every vast cosmic web of filaments and voids that stretches across billions of light years, all of it grew from those barely there ripples in the primordial plasma. And the mechanism that amplified those seeds, that turned whispers into thundering architecture, is gravity. Just plain gravity. The same force that keeps your feet on the ground, the same curvature of space-time Einstein described. That's the sculptor. But it needed time, and it needed those initial imperfections to work with. So picture the universe right after recombination, about 380,000 years old. The cosmic microwave background has just been released, photons streaming freely for the first time, and what's left behind is a vast, cooling gas of mostly hydrogen and helium. And this gas is almost perfectly uniform. Almost. But in some regions, the density is just a tiny bit higher than average, maybe 1 part in 100,000 higher. That's it. That's the seed. 1 part in 100,000. If you had a perfectly smooth lake and you dropped a single grain of sand into it, the ripple you'd get would be proportionally enormous compared to these density fluctuations. They're unbelievably subtle. But here's the thing about gravity. It's patient, and it's relentless, and it has a built-in feedback loop. If a region of space has slightly more matter than its surroundings, it pulls on nearby matter just a little more strongly. That extra matter increases the gravitational pull further, which draws in even more matter, which increases the pull again. Physicists call this gravitational instability, or sometimes Jeans instability, after the British physicist James Jeans, who worked out the mathematics of it way back in 1902. Jeans showed that if you have a cloud of gas above a certain critical size, now called the Jeans length, gravity will overwhelm the gas's internal pressure, and the cloud will start to collapse. Below that size, pressure wins, and the cloud just oscillates, like a sound wave. Above it, gravity wins, and the cloud contracts. And that's exactly what happened. After recombination, the universe was suddenly transparent, and the photons that had been providing radiation pressure, keeping the plasma from collapsing, were gone. They'd decoupled. So now you had this gas, and the only things fighting gravity were the thermal pressure of the gas itself, which was dropping as the universe cooled, and the expansion of space, which was working against collapse by stretching everything apart. It's a tug of war. Gravity pulling matter together, expansion pulling it apart. And in regions where the density was just slightly above average, gravity had the edge. Now, here's where dark matter becomes absolutely essential to the story, and where it connects back to everything we talked about earlier. ordinary matter, the hydrogen and helium, couldn't start collapsing on its own early enough. Before recombination, ordinary matter was locked to the photons in that hot plasma, and the radiation pressure prevented it from clumping. But dark matter doesn't interact with photons. It doesn't care about radiation pressure at all. So dark matter started collapsing earlier, while ordinary matter was still trapped in the plasma, being buffeted by photon pressure. Dark matter was quietly, invisibly, pulling itself together into denser and denser clumps. By the time recombination happened and ordinary matter was finally free to fall, dark matter had already built a scaffolding, a network of gravitational wells, like valleys in a landscape, waiting for the ordinary matter to tumble into them. Think about that for a second. Without dark matter, the tiny fluctuations in the cosmic microwave background would have taken far, far longer to grow into anything recognizable. The universe might still be a thin, diffuse gas today. The fact that we're here, that galaxies exist, that stars formed early enough for life to emerge, that depends critically on dark matter getting a head start. It's one of the strongest indirect arguments for dark matter's existence. When cosmologists run computer simulations of structure formation, and these are extraordinary simulations, some of the largest computations ever performed, tracking billions of particles across cosmic time. The ones that include dark matter produce universes that look like ours. The ones that don't. One of the most famous of these simulations is called the Millennium Simulation, run in 2005 by a team led by Volker Springel at the Max Planck Institute in Germany. It tracked 10 billion dark matter particles in a cube of space, about 2 billion light-years on a side, evolving them forward from shortly after the Big Bang to the present day. And what emerged was stunning. Dark matter formed a cosmic web, a vast, sponge-like network of filaments and nodes, with huge, empty voids in between. The filaments are like highways of dark matter, and at the intersections where multiple filaments meet, you get the densest concentrations. And that's where the biggest galaxy clusters form. The voids, by contrast, are vast regions of nearly empty space, some of them hundreds of millions of light-years across. And when astronomers look at the actual distribution of galaxies in the real universe, through surveys like the Sloan Digital Sky Survey, which has mapped the positions of millions of galaxies, the pattern matches. Galaxies aren't scattered randomly. They're arranged in filaments and walls and clusters, with enormous voids between them, exactly the way the simulations predict. It's one of the great triumphs of modern cosmology, this agreement between simulation and observation. You start with the tiny fluctuations measured in the cosmic microwave background. You add the known physics of gravity and expansion and dark matter. You run it forward 13 billion years, and you get something that looks like the universe we actually see. That's remarkable. But let's slow down and think about what's actually happening inside one of those collapsing regions, because the process of going from a slightly denser patch of gas to an actual galaxy with stars and planets, that's not simple. First, the dark matter collapses and forms what's called a halo, a roughly spherical cloud of dark matter held together by its own gravity. Then, ordinary matter, the hydrogen and helium, falls into the gravitational well of the dark matter halo. As it falls in, it gets compressed and heats up. And here's a crucial difference between dark matter and ordinary matter. Ordinary matter can radiate. It can emit photons and cool down. Dark matter can't. It doesn't interact electromagnetically, so it can't shed energy as light. This means ordinary matter can lose energy, sink deeper into the gravitational well, and become much more concentrated than the dark matter. The dark matter stays as a diffuse halo. The ordinary matter collapses further, forming a dense disk or cloud at the center. And within that cloud, smaller regions become dense enough to collapse under their own gravity, and those become stars. So you've got this beautiful nested structure. Dark matter halos, big and diffuse, providing the gravitational framework. Inside them, ordinary matter cooling and condensing into galaxies. Inside those galaxies, individual clouds of gas collapsing into stars, and inside those stars, nuclear fusion igniting, forging heavier elements, which, remember, is where your atoms came from. The carbon in your cells, the iron in your blood, all cooked up in the cores of stars that formed inside galaxies that formed inside dark matter halos that grew from quantum fluctuations in the early universe. That chain of causation is real. It's not poetry. It's physics. Now, this process didn't happen everywhere at the same time. Structure formation is hierarchical. Small things form first, and then merge into bigger things. Small dark matter halos collapse first, and then they merge with other small halos to form larger ones. Small galaxies form first, and then collide and merge to form bigger galaxies. Our own Milky Way has absorbed dozens of smaller galaxies over its lifetime, and you can still see the evidence. Streams of stars in the galactic halo that are the stretched-out remnants of galaxies we consumed. And the Milky Way itself is on a collision course with the Andromeda Galaxy. In about 4.5 billion years, the two will merge into a single, larger galaxy. Astronomers sometimes call the future result Milkomeda, which is a bit whimsical, but the event itself will be real enough. Here's something counterintuitive about galaxy collisions, though. When the Milky Way and Andromeda merge, almost no stars will actually collide with each other. Stars are tiny compared to the distances between them. If you shrank the sun down to the size of a grain of sand, the nearest other grain of sand would be about 4 miles away. So when two galaxies pass through each other, the stars mostly just sail past one another. What does change dramatically is the gas. Gas clouds do collide, and when they do, they compress and heat up, and that can trigger enormous bursts of star formation. Some of the most spectacular star-forming galaxies we've ever observed are galaxy mergers caught in the act, blazing with the light of millions of newborn stars. But let's come back to the early universe for a moment, because there's a mystery here that took decades to sort out, and it connects to one of the deepest ideas in all of physics. We said that structure grew from tiny density fluctuations in the early universe. But where did those fluctuations come from? Why wasn't the early universe perfectly smooth? What broke the symmetry? And the answer, or at least our best answer, is extraordinary. Those fluctuations appear to be quantum mechanical in origin. They come from the same fundamental uncertainty that governs the behavior of subatomic particles. In the very earliest moments of the universe, when everything was compressed into an unimaginably tiny volume, quantum fluctuations, the random, inherent jitteriness of fields at the smallest scales, were happening constantly. Normally, quantum fluctuations are inconceivably small, operating at scales far tinier than an atom. But something happened in the first sliver of a second after the Big Bang that took those microscopic fluctuations and stretched them to cosmic proportions. That something is called inflation. Inflation is one of the most audacious ideas in all of cosmology. It was proposed in 1980 by a young physicist named Alan Guth, who was working at the Stanford Linear Accelerator Center at the time, and he was actually trying to solve a completely different problem. he wasn't thinking about the origin of structure at all. He was thinking about something called the magnetic monopole problem, a prediction from particle physics that the early universe should have produced enormous numbers of magnetic monopoles, hypothetical particles that carry isolated north or south magnetic poles. The problem was that nobody had ever found one. Not a single magnetic monopole had ever been detected, despite the theory predicting they should be everywhere. Guth realized that if the universe had undergone a brief period of extraordinarily rapid expansion very early on, far faster than the normal expansion rate, it would dilute the monopoles to the point where you'd never expect to find one in the observable universe. Problem solved. But then he and others realized that this same rapid expansion would solve two other major puzzles simultaneously. The first is called the horizon problem, the question of why the cosmic microwave background has almost exactly the same temperature in every direction, even in regions of the sky that, in the standard Big Bang model, could never have been in causal contact with each other. They're too far apart for light to have traveled between them in the age of the universe. So how did they reach the same temperature? Inflation answers this by saying that before inflation, those regions were actually very close together, close enough to reach thermal equilibrium. Then inflation stretched them enormously far apart, but they retained the memory of that earlier contact. The second puzzle is the flatness problem. Observations show that the geometry of the universe is very close to flat, meaning parallel lines stay parallel. Triangles have angles that add up to 180 degrees, all the familiar Euclidean stuff. But in the standard Big Bang model, flatness is an unstable condition. Any tiny deviation from perfect flatness in the early universe would have been amplified over time, driving the universe toward either extreme positive or extreme negative curvature. For the universe to be as flat as we observe it today, it would have had to start out flat to an almost absurd degree of precision, something like 1 part in 10 to the 60. That's not an explanation. That's a coincidence screaming for an explanation. And inflation provides one because the rapid expansion drives the geometry toward flatness automatically, the same way inflating a balloon makes its surface look flatter and flatter the bigger it gets. So inflation solves the monopole problem, the horizon problem, and the flatness problem, all in one stroke. And as a bonus, and this is the part that connects back to where we started, inflation takes quantum fluctuations and stretches them to macroscopic scales. Those tiny random quantum jitters in the field that drove inflation get frozen in as the universe expands, becoming the density fluctuations that we later see imprinted in the cosmic microwave background. The seeds of all structure in the universe, every galaxy, every star, every planet, every person, may trace back to quantum uncertainty in the first tiny fraction of a second. And here's what's really compelling about this. Inflation makes specific, testable predictions about the statistical properties of those fluctuations, their spectrum, their distribution, how they should vary with scale. And when the Planck satellite measured the cosmic microwave background with exquisite precision, the pattern of fluctuations matched inflation's predictions beautifully. Not perfectly. There are a few anomalies that people argue about. But the overall agreement is striking. Now, inflation itself raises questions. What is the field that drove it? What triggered it to start, and what caused it to stop? There are hundreds of different inflationary models, and distinguishing between them is one of the great challenges of modern cosmology. Some physicists, like Paul Steinhardt at Princeton, who was actually one of inflation's early developers, have become skeptical of the whole framework, arguing that it's become so flexible it can accommodate almost any observation and therefore doesn't really predict anything. That's a serious criticism, and the debate is ongoing. But most cosmologists still regard inflation, or something very like it, as the best explanation we have for the large-scale properties of the universe. And there's one more prediction of inflation that hasn't been confirmed yet, but that people are searching for intensely. Inflation should have generated gravitational waves, ripples in space-time itself, at the very beginning. These primordial gravitational waves would leave a distinctive imprint in the polarization of the cosmic microwave background, a swirling pattern called B-mode polarization. In 2014, a team using a telescope called BICEP-2 at the South Pole announced that they'd found this signal, and for a brief, thrilling moment, it seemed like inflation had been directly confirmed. But it turned out that the signal was mostly, possibly entirely, caused by dust in our own galaxy, mimicking the expected pattern. It was a heartbreaking false alarm. But the search continues, with more sensitive experiments, because if primordial gravitational waves are ever definitively detected, it would be one of the most profound discoveries in the history of science. Direct evidence of quantum gravity, of the universe's behavior at energies we could never hope to reach in any laboratory. Which brings us to something that's been lurking in the background of everything we've talked about so far: the relationship between the very large and the very small, between gravity and quantum mechanics, between the cosmos and the atom. Because here's the uncomfortable truth at the heart of modern physics. Our two greatest theories, general relativity and quantum mechanics, are each spectacularly successful in their own domain, and yet they are fundamentally incompatible with each other. They describe the universe in ways that, when you try to combine them, produce nonsense. And the story of how physicists have grappled with that incompatibility, the quest for a theory of quantum gravity, is one of the most fascinating and frustrating stories in all of science. Because it's not just an academic puzzle. It's the reason we don't understand what happens at the center of a black hole. It's the reason we can't describe the very first instant of the Big Bang. It's the reason the deepest questions about the universe, what is space really? What is time really? Remain unanswered. And to understand why these two theories clash so badly, you need to understand what each one actually says about the nature of reality, because they say very different things. General relativity, Einstein's masterpiece from 1915, tells us that space and time are not a fixed stage on which things happen. They're dynamic. They bend, they stretch, they warp in response to mass and energy. Gravity isn't a force pulling you down. It's the curvature of space-time itself guiding your motion. The Earth doesn't pull you toward it, so much as the mass of the Earth curves the space-time around it, and you follow that curve. It's a smooth, continuous, deterministic theory. Given perfect knowledge of the mass and energy in a region, you can calculate exactly how space-time curves and exactly how objects will move through it. It's elegant. It's geometric, and it works phenomenally well for planets, stars, galaxies, the expansion of the universe, anything large and massive. Quantum mechanics, developed in the 1920s by a whole cast of characters, Heisenberg, Schrödinger, Dirac, Born, Bohr, Pauli, tells us something completely different about reality. At the smallest scales, the world is not smooth and deterministic. It's grainy, probabilistic, and deeply strange. Particles don't have definite positions until you measure them. They exist in superpositions of multiple states simultaneously. They can tunnel through barriers they shouldn't be able to cross. And there's a fundamental limit, Heisenberg's uncertainty principle, on how precisely you can know certain pairs of properties at the same time, like position and momentum. The more precisely you pin down one, the more the other smears out. This isn't a limitation of your instruments, it's a feature of reality itself, and quantum mechanics works spectacularly well for atoms, electrons, photons, quarks, anything tiny. So you've got two theories. One governs the very large, the other governs the very small, and each one has been tested to extraordinary precision. General relativity predicted gravitational waves, and we detected them in 2015 with LIGO, matching the predictions to astonishing accuracy. Quantum mechanics predicts the magnetic moment of the electron to about 10 decimal places, and experiment confirms it to about 10 decimal places. These are arguably the two most successful theories in the history of science, and they cannot both be right, at least not in their current forms, because they describe the fabric of reality in fundamentally incompatible ways. Here's where the trouble shows up most clearly. In general relativity, space-time is a smooth, continuous fabric. You can always zoom in further, and it stays smooth. In quantum mechanics, everything at small scales is subject to quantum fluctuations, jittery, and uncertain. So what happens when you try to apply quantum mechanics to space-time itself? What happens when you try to describe gravity at the quantum level? You get infinities. Not useful infinities that you can handle with clever mathematical tricks. Physicists actually do that all the time in quantum field theory. It's called renormalization, and it works beautifully for the electromagnetic force and the strong and weak nuclear forces. But when you try to renormalize gravity, the infinities multiply and cascade, and the whole mathematical framework collapses into gibberish. The theory becomes, in the technical language, non-renormalizable. It doesn't just give you wrong answers, it gives you no answers at all. Now, for most practical purposes, this doesn't matter. Gravity is so incredibly weak compared to the other forces. And this is something people don't always appreciate, how absurdly weak gravity is. Think about it this way. A tiny refrigerator magnet can hold up a paperclip against the gravitational pull of the entire Earth. The electromagnetic force in that little magnet is overpowering the gravity of a planet with a mass of 6 trillion kilograms. Gravity is roughly 10 to the 36th power times weaker than electromagnetism. So in the quantum world of atoms and particles, gravity is utterly negligible. You can just ignore it, and quantum mechanics works fine. And in the world of planets and stars and galaxies, quantum effects are negligible, and general relativity works fine. The two theories almost never need to talk to each other. Almost never. But there are situations, extreme situations, where both quantum effects and gravitational effects are simultaneously important, where you need both theories at once. And those are exactly the situations where our understanding breaks down completely. The most obvious one is the singularity at the center of a black hole. General relativity predicts that when a massive star collapses, all its matter gets crushed into a single point of infinite density, a singularity. But infinite density means you're packing a finite amount of mass into zero volume, which means you're in the quantum regime, where quantum effects absolutely cannot be ignored. Yet we have no quantum theory of gravity to tell us what actually happens there. The singularity isn't really a prediction, it's a confession. It's general relativity raising its hand and saying, I've reached my limit, I can't describe this, someone else needs to take over. And there's no one to take over. The same thing happens at the very beginning of the universe. Run the expansion backward, and general relativity says the entire observable universe was once compressed into a point of infinite density and temperature. The the Big Bang singularity. But again, at those scales, quantum effects dominate, and we have no theory that can handle both. So when people ask, what happened before the Big Bang? Or what caused the Big Bang? Or what was the Big Bang really like in its first instant? The honest answer is, we don't know, because our physics breaks down there. The first tiny fraction of a second, specifically the first Planck time, which is about 5.4 times 10 to the negative 44 seconds, is hidden behind a wall of ignorance. And that wall is the incompatibility of general relativity and quantum mechanics. The Planck scale is worth pausing on for a moment because it tells you exactly where the trouble lives. In the late 1800s, Max Planck, the same Planck whose name is on the satellite that mapped the CMB, realized that you could combine three fundamental constants of nature: the gravitational constant g, the speed of light c, and the quantum constant h bar, called h bar, to create natural units of length, time, mass, and energy. The Planck length is about 1.6 times 10 to the negative 35 meters. That's absurdly small. If an atom were the size of the observable universe, the Planck length would be roughly the size of a tree. The Planck energy, on the other hand, is enormous, about 10 to the 19 billion electron volts, or roughly the energy of a tank of gasoline compressed into a single particle. These are the scales at which quantum gravitational effects should become dominant. And they are so far beyond anything we can probe experimentally that it sometimes feels like nature is deliberately hiding the answer from us. So how have physicists tried to crack this problem? Well, the most famous attempt, and the one you've probably heard of, is string theory. The basic idea emerged in the late 1960s and early 1970s, originally in a completely different context. People were trying to understand the strong nuclear force, and a young physicist named Gabriele Veneziano found a mathematical formula in 1968 that described certain patterns in particle collisions surprisingly well. It turned out that this formula could be interpreted as describing not point particles, but tiny vibrating strings. The idea didn't work very well for the strong force. Quantum chromodynamics, or QCD, turned out to be the right theory for that. But a few physicists noticed something remarkable. If you included a certain type of vibration, the theory naturally produced a massless particle with spin 2, and there's only one massless spin 2 particle that makes physical sense: the graviton, the hypothetical quantum carrier of gravity. This was a stunning accident. You start with vibrating strings, and gravity falls out automatically. John Schwartz and Joel Shirk made this connection explicit around 1974, arguing that string theory wasn't a theory of the strong force at all. It was a theory of everything, including gravity. But almost nobody paid attention. The physics community was focused on the Standard Model, which was having spectacular success explaining the electromagnetic weak and strong forces. String theory seemed like an exotic curiosity, mathematically interesting but physically irrelevant. That changed in 1984, during what's called the first superstring revolution. Schwartz and Michael Green showed that a particular version of string theory, type 1 superstring theory, was free of certain mathematical inconsistencies called anomalies that had plagued earlier attempts. This was a technical result, but its implications were enormous. It meant string theory was mathematically consistent as a quantum theory that included gravity. For the first time, there was a framework that could, at least in principle, describe all four fundamental forces: gravity, electromagnetism, the strong force, and the weak force, in a single unified theory. Suddenly, string theory went from a backwater to the hottest topic in theoretical physics. Edward Witten, widely regarded as the most brilliant physicist of his generation, threw his weight behind it, and hundreds of talented young physicists followed. But here's the thing about string theory. It requires extra dimensions. Not 3 dimensions of space and 1 of time, but 9 dimensions of space and 1 of time. 10 dimensions total, or 11 in the version called M theory that Witten proposed in 1995. The extra 6 or 7 dimensions are supposed to be compactified, curled up so small that we can't see them, perhaps at the Planck scale. And the way these extra dimensions are curled up determines the physics we observe. The masses of particles, the strengths of forces, everything. The problem is that there are an astronomically large number of ways to curl up those extra dimensions. Estimates suggest something like 10 to the 500 possible configurations, each one giving rise to a different version of low-energy physics. This is the string theory landscape, and it's both the theory's greatest feature and its greatest embarrassment. Because if there are 10 to the 500 possible universes, and string theory doesn't tell you which one is ours, then what exactly is it predicting? This is the criticism that has dogged string theory for decades. People like Lee Smolin and Peter Woit have argued, sometimes quite forcefully, that string theory has become unfalsifiable, that it can accommodate almost any observation, which means it predicts almost nothing specific. Supporters counter that the theory has produced deep mathematical insights, has taught us profound things about black holes and quantum information, and that we simply haven't understood it well enough yet to extract its predictions. The debate is genuine and ongoing, and reasonable people disagree. And string theory isn't the only game in town. There's another approach called loop quantum gravity, developed primarily by Abhay Ashtekar, Carlo Rovelli, and Lee Smolin, starting in the late 1980s. Loop quantum gravity takes a very different philosophical stance. Instead of trying to unify all the forces into one framework, it focuses specifically on quantizing gravity, on applying quantum mechanics to space-time itself, and it does so without requiring extra dimensions or strings. The central idea is that space, at the Planck scale, is not continuous. It's made of discrete, granular units, tiny loops of gravitational field woven together into a structure called a spin network. Think of it like a fabric that looks smooth from a distance, but if you could zoom in far enough, you'd see it's made of individual threads with gaps between them. Space has a smallest possible volume, roughly 1 Planck length cubed, and area has a smallest possible unit. You literally cannot have a distance smaller than the Planck length, just as you cannot have less than 1 quantum of energy in a given mode. This discreteness of space has a beautiful consequence. It eliminates the singularities that plague general relativity. If space can't be compressed below a certain size, then you can't crush matter into a point of infinite density. The Big Bang singularity gets replaced by what's sometimes called a big bounce. The universe might have contracted from a previous phase, reached a minimum size dictated by quantum gravity, and then expanded again. It's a tantalizing idea, and loop quantum gravity has made it mathematically precise in simplified models. But like string theory, it faces enormous challenges. It's very difficult to show that loop quantum gravity reproduces general relativity in the appropriate limit. That is, that the smooth spacetime we observe emerges naturally from the underlying quantum granularity, and it doesn't naturally incorporate the other forces of nature the way string theory attempts to. So we're in this remarkable situation where the two leading candidates for quantum gravity, string theory and loop quantum gravity, each have profound strengths and profound weaknesses, and neither one has made a prediction that's been experimentally confirmed. Some physicists find this frustrating. Others find it exhilarating, because it means the deepest question in fundamental physics is still genuinely open. The answer, when it comes, could reshape our understanding of space, time, and reality itself. And there's another angle on this whole puzzle that's become increasingly important in recent years, one that connects quantum gravity to something you might not expect: information. Specifically, what happens to information when it falls into a black hole. Because in 1974, Stephen Hawking showed something that shook the foundations of physics in a way nobody saw coming. He showed that black holes aren't truly black. They glow. Faintly, incredibly faintly. But they radiate energy, and over unimaginably long timescales, they evaporate, they shrink, and eventually, they disappear entirely. Now let that settle for a moment, because this was genuinely shocking. Everything physicists thought they knew about black holes said that nothing escapes. That's the whole point of a black hole. The gravity is so intense that once something crosses the event horizon, it's gone. Light can't get out. Matter can't get out. Nothing gets out. And yet here was Hawking, using a careful calculation that blended quantum mechanics with general relativity. Not a full theory of quantum gravity, mind you, but a kind of semi-classical approximation. And the math was telling him that black holes emit a steady trickle of particles. Thermal radiation, like the glow of a warm object, but at an extraordinarily low temperature. Here's how to think about it. You remember how quantum mechanics says the vacuum isn't really empty? It's a seething froth of virtual particle pairs popping into existence and annihilating each other almost instantly. Normally, this is just background noise, invisible and inconsequential. But near the event horizon of a black hole, something strange happens. A pair of virtual particles can form right at the edge, and before they have a chance to recombine and vanish, the tidal forces of the black hole can pull them apart. One particle falls in, the other escapes. The escaping particle carries real energy away from the black hole, and that energy has to come from somewhere. So it comes from the black hole's mass. The black hole gets a tiny bit lighter, a tiny bit smaller. And this happens over and over and over. For a black hole with the mass of our sun, this radiation is so feeble. The temperature is something like 60 billionths of a degree above absolute zero, that it would take something like 10 to the 67th years to evaporate. That's a number so large, it makes the current age of the universe look like a blink. So in any practical sense, stellar mass black holes aren't evaporating anytime soon. But the principle is what matters. Given enough time, every black hole will eventually radiate away all of its mass and vanish. And that's where the crisis begins. Because think about what a black hole has swallowed over its lifetime. Stars, gas clouds, planets, maybe. Each of those things was made of specific particles in specific arrangements, carrying specific information about what they were. The quantum state of every atom, every electron, every photon that fell in. All of that information crossed the event horizon and, according to classical general relativity, ended up at the singularity. Now, quantum mechanics has a sacred principle called unitarity, which basically says that information is never truly destroyed. It can be scrambled, it can be rearranged into a form you'd never recognize, but it's always there in principle. If you had a powerful enough computer and complete knowledge of the current state of a system, you could in theory reconstruct its entire history. Nothing is lost. But if a black hole evaporates completely, and the radiation it emits is perfectly thermal, perfectly random, carrying no information about what fell in, then all that information is just gone, erased from the universe. And that violates unitarity. That breaks quantum mechanics. This is the black hole information paradox, and it has consumed theoretical physics for half a century now. Hawking himself initially argued that the information really was destroyed, that this was simply a new feature of quantum gravity. He was quite firm about it, actually. In 1981, he gave a famous talk at a conference in San Francisco, where he laid out the case plainly. Black hole evaporation destroys information, and we need to accept that. Most of the quantum mechanics community was horrified. If information can be destroyed in black holes, then the entire mathematical framework of quantum theory starts to unravel. The equations stop being consistent. The person who pushed back hardest was probably Leonard Susskind, the Stanford physicist. Susskind and his colleague Gerard 't Hooft, the Dutch Nobel laureate, spent years developing counterarguments. Their position was that information must be preserved, that it somehow gets encoded in the Hawking radiation, even if we don't understand the mechanism yet. The disagreement between Hawking and Susskind became one of the great intellectual rivalries of late 20th century physics. Susskind later wrote a whole book about it called The Black Hole War, and the title isn't much of an exaggeration. This was a genuine battle over the foundations of physics, fought with thought experiments and mathematical arguments over decades. And here's where things get really interesting, because the attempts to resolve this paradox have led to some of the most mind-bending ideas in all of physics. One of the most important is the holographic principle. This idea, which grew out of the work of 't Hooft and Susskind in the early 1990s, suggests something almost absurd: that all the information contained within a volume of space can be described by a theory that lives on the boundary of that space. Think about that. Everything happening in a three-dimensional room, every particle, every interaction, every bit of information, could in principle be encoded on a two-dimensional surface surrounding that room, like a hologram, where a flat piece of film contains all the information needed to reconstruct a three-dimensional image. This sounds like science fiction, but in 1997, a young Argentine-American physicist named Juan Maldacena made it mathematically precise. He was at Harvard at the time, just 30 years old, and he published a paper that has since become the most cited paper in the history of high-energy physics. What Maldacena showed was a specific, concrete example of the holographic principle, a duality, a mathematical equivalence, between a theory of gravity in a particular kind of curved space-time and a quantum field theory without gravity living on the boundary of that space-time. It's called the ADS/CFT correspondence, and if those letters don't mean anything to you, don't worry about them. What matters is the idea. A universe with gravity can be completely equivalent to a universe without gravity that has one fewer dimension. They're the same theory written in two different languages. Now you might be thinking, okay, that's mathematically elegant, but does it actually solve the information paradox? And the answer is, kind of, yes. In the boundary theory, the one without gravity, there's no black hole, and information is manifestly preserved. Unitarity holds. So if the two descriptions are truly equivalent, then information must also be preserved in the gravitational description, even though we can't easily see how. The information gets out. It has to. It's encoded in the Hawking radiation in some fantastically scrambled form. Hawking himself eventually came around. In 2004, at a conference in Dublin, he conceded the bet he'd made with Kip Thorne against John Preskill, a bet about whether information was truly lost. Hawking admitted he'd been wrong. Information is preserved. He even presented a calculation, though many physicists found his specific argument unconvincing. The concession itself was what mattered. Even Hawking now agreed that quantum mechanics wins. But, and this is important, the paradox isn't fully resolved. We know information gets out, but we still don't really understand the mechanism in detail. And in 2012, a group of physicists, Ahmed Almheri, Donald Maroff, Joseph Polchinski, and James Sully, usually called AMPS after their initials, showed that the most natural ways of preserving information lead to another terrible problem. If information is encoded in the Hawking radiation, and that radiation is entangled with the interior of the black hole in the way quantum mechanics requires, then something has to break at the event horizon. An infalling observer wouldn't experience the smooth passage through the horizon that general relativity predicts. Instead, they'd hit a wall of high-energy particles, a firewall, and be incinerated. This was disturbing because the whole point of general relativity's equivalence principle is that an observer falling through the event horizon shouldn't notice anything special. Locally, crossing the horizon should feel like floating in empty space. The firewall argument said no, that can't be right. Not if you want to preserve information and maintain the rules of quantum mechanics. So now, you've got three things that physicists hold dear: unitarity, the equivalence principle, and the smoothness of space-time at the horizon. And the AMPS argument says you can't have all three. You have to give up at least one, and nobody wants to give up any of them. This is where the field sits right now, more or less. There have been fascinating developments, ideas about quantum error correction, about the entanglement structure of space-time itself, about something called the Page curve, and recent calculations by Jeff Pennington, Netta Engelhardt, Ahmed Almheri, and others that use a concept called quantum extremal surfaces to show that the entropy of Hawking radiation does eventually decrease, just as unitarity demands. These calculations, published around 2019 and 2020, were widely regarded as a major breakthrough because they derived the right answer. Information comes out using tools from semi-classical gravity without needing a complete theory of quantum gravity. But even these results rely on the ADS/CFT framework, and our actual universe doesn't have the geometry that ADS/CFT describes. Our universe has a positive cosmological constant. It's expanding, accelerating, dominated by dark energy. The space-time Muldasena studied has a negative cosmological constant. So there's this lingering question: does the holographic principle apply to our universe? And if so, how? This is one of the deepest open questions in all of physics, and it connects back to something we talked about much earlier: the accelerating expansion of the universe, the dark energy that Perlmutter, Schmidt, and Rees discovered in 1998. Because the cosmological constant doesn't just affect the fate of the universe. It affects the fundamental structure of the theory we need to describe it. A universe with a positive cosmological constant, a de Sitter universe as it's called, after the Dutch physicist Willem de Sitter, has a cosmological horizon. There's a maximum distance from which light can ever reach you, because space beyond that distance is receding faster than light can travel. And that horizon, like a black hole's event horizon, has thermodynamic properties. It has a temperature. It has an entropy. Hawking and Gary Gibbons showed this back in 1977. So in a sense, we're all living inside something that behaves a little like a black hole turned inside out. The horizon isn't surrounding a singularity at the center. It's surrounding us, way out at the edges of the observable universe. And it radiates, just like a black hole does, at an incredibly low temperature. The implications of this for quantum gravity, for the holographic principle, for the nature of information and entropy. These are questions that the best minds in physics are actively wrestling with right now. And it turns out that this whole conversation about information, entropy, and horizons connects to something even more fundamental, something about the nature of space-time itself. Because there's a growing suspicion among many physicists, a suspicion that's been building for about a decade now, that space-time isn't fundamental at all, that space and time are emergent. They arise from something deeper, something more basic, the way temperature arises from the motion of molecules. You don't find temperature in any individual molecule. It's a collective property, a statistical description. And some physicists now believe that space-time works the same way, that what we experience as the smooth fabric of space and time is actually woven from something else entirely, and the thread that does the weaving might be quantum entanglement. That strange, almost spooky connection between particles that Einstein himself found so deeply unsettling that he called it spukhafte Fernwirkung, spooky action at a distance. And to understand why entanglement might be the thread from which space-time is woven, we need to sit with this idea for a moment, because it's one of the most profound shifts in thinking about the universe that's happened in the last 20 years. You already know the basic idea of entanglement. Two particles interact, and after that interaction, their quantum states are linked. You measure one, and you instantly know something about the other, no matter how far apart they are. Einstein hated this. He and Boris Podolsky and Nathan Rosen wrote their famous EPR paper in 1935, arguing that entanglement proved quantum mechanics was incomplete, that there must be hidden variables, some deeper layer of reality that would explain the correlations without requiring this bizarre, instantaneous connection. But decades of experiments, starting with John Bell's theoretical framework in 1964 and Alan Aspect's landmark experiments in Paris in 1982, showed that no, the correlations are real, they're not explained by hidden variables, and entanglement is genuinely a feature of nature. It's not a bug, it's how the universe actually works. But here's the thing that nobody expected. For most of the 20th century, entanglement was treated as a property of quantum mechanics, something that mattered for particles, for atoms, for quantum information. Nobody thought it had anything to do with gravity or the shape of space-time. Those were separate departments, separate chalkboards, separate conferences. Quantum mechanics over here, general relativity over there, and never the twain shall meet. But then, starting around 2006, a physicist named Mark van Ramsdonk at the University of British Columbia started asking a question that sounds almost naive when you first hear it. He asked, "What happens to space-time when you remove entanglement?" And the answer he found, working within the framework of Maldaceno's ADS/CFT correspondence, that duality between a gravitational theory in the bulk and a quantum theory on the boundary that we talked about earlier. The answer was startling. If you take two regions of the boundary theory and you gradually reduce the entanglement between them, the corresponding region of space-time in the bulk starts to pinch off. It's like pulling apart a piece of taffy. As the entanglement decreases, the spatial connection gets thinner and thinner, and if you remove the entanglement entirely, the space-time splits in two. It literally disconnects two separate universes where there used to be one. Think about what that means. It means that the thing holding space-time together, the glue, if you want to think of it that way, is entanglement. Without entanglement, there's no spatial connection. Space itself is a manifestation of quantum correlations between degrees of freedom on some more fundamental level. Van Ramsdonk published a beautiful paper in 2010 called Building Up Space-Time with Quantum Entanglement, and it was one of those papers that shifted the conversation in the field. Not everyone was convinced immediately, of course. That's not how physics works. But a lot of people sat up and paid attention. And this connected to another beautiful idea that had been floating around. An idea about Einstein-Rosen bridges, what we usually call wormholes. Back in 1935, the same year Einstein, Podolsky, and Rosen published their paper about entanglement, Einstein and Rosen published a completely separate paper about what they called bridges in spacetime, solutions to the equations of general relativity, where two black holes are connected by a tunnel through the fabric of space. Two papers, same year, same lead author, seemingly about completely different things. One about quantum entanglement, one about geometric connections in spacetime. And for almost 80 years, nobody thought they were related. Then in 2013, Juan Maldacena, the same Maldacena who gave us ADS/CFT, teamed up with Leonard Susskind, and they proposed something audacious. They proposed that these two phenomena are actually the same thing. That an Einstein-Rosen bridge, a wormhole, is simply entanglement viewed from the gravitational side of the duality. They wrote it as an equation, almost a slogan, ER equals EPR. Einstein-Rosen equals Einstein-Podolsky-Rosen. Wormholes equal entanglement. The geometric connection through spacetime that we call a wormhole is, in some deep sense, identical to the quantum correlation we call entanglement. Now, this is one of those ideas that either makes you furrow your brow skeptically or makes the hair on the back of your neck stand up. Maybe both at the same time. Because if it's right, it means that every entangled pair of particles in the universe is connected by a tiny, microscopic wormhole. Not a wormhole you could travel through, nothing like science fiction, but a fundamental geometric link in the deep structure of spacetime, and the smooth, continuous space that you and I move through every day, the space between your pillow and the wall, the space between Earth and the moon. That smoothness emerges from the collective effect of vast numbers of these entanglement connections, all woven together into what we experience as geometry. It's like, okay, think about a piece of fabric, a cotton shirt, say. From a distance it looks smooth and continuous, but get close enough and you see it's made of threads. Get closer still and you see the threads are made of fibers. The smoothness is an illusion that emerges from the underlying structure. ER equals EPR suggests that spacetime works the same way. The smooth geometry of general relativity is what you get when you zoom out from a vast network of quantum entanglement. And the equations of gravity, Einstein's beautiful field equations, the ones he struggled for years to find, might be, in some sense, a thermodynamic description of this underlying quantum information, the way the laws of fluid dynamics are a thermodynamic description of the motion of molecules. This connects back to something we touched on earlier, something Ted Jacobson noticed all the way back in 1995. Jacobson, a physicist at the University of Maryland, showed that you could derive Einstein's field equations, actually derive them, not just postulate them, from thermodynamic relationships. Specifically, from the relationship between entropy and area that Bekenstein and Hawking had established for black holes. If you assume that entropy is proportional to area for any causal horizon, not just a black hole horizon, and you apply the basic laws of thermodynamics, Einstein's equations pop out. They're not fundamental. They're emergent. They're the macroscopic description of something deeper, the way pressure and temperature are macroscopic descriptions of molecular motion. And Erik Verlinde, a Dutch theoretical physicist at the University of Amsterdam, pushed this even further in 2010 with his proposal of entropic gravity. Verlinde argued that gravity itself, the force that keeps your body pressed against your mattress right now, the force that holds the moon in orbit, the force that shaped every galaxy in the observable universe, might not be a fundamental force at all. It might be an entropic force, something that arises statistically from the tendency of systems to move toward states of higher entropy. Think of it this way. When you drop a ball, it falls not because some fundamental graviton is pulling it, but because the configuration where the ball is lower corresponds to more microscopic arrangements of the underlying quantum information, so the system naturally evolves in that direction. It's controversial. Many physicists have serious objections, but the fact that you can even formulate the idea coherently, that the mathematics works out at least in certain cases, that tells you something deep is going on. So let's step back and take in the view from here, because it's quite something. We started this whole journey talking about the universe on its largest scales, the expansion of space, the cosmic microwave background, the web of galaxies stretching across billions of light years. And now we've arrived at a place where the best ideas in theoretical physics are suggesting that all of that, all of space, all of time, all of gravity, might emerge from quantum information, from qubits, from entanglement. The universe might be, at its most fundamental level, a quantum computer of sorts. Not a computer in the sense of a machine that someone built to calculate things, but a system whose deepest description is in terms of information and its processing. John Wheeler, who we met much earlier in our story, the man who coined the term black hole, who mentored a generation of physicists, including Kip Thorne and Richard Feynman's doctoral work, Wheeler spent the last decades of his life championing an idea he called it from bit. The idea that every physical quantity, every it, derives its existence from information, from bits. He proposed this in the early 1990s, and at the time, most physicists thought it was poetic but vague. Now, 3 decades later, the field is converging on something remarkably close to what Wheeler intuited, except now they'd probably update it to it from qubit, because the information that matters is quantum information, not classical. And here's where this connects to something practical, something that might affect your life within the next few decades. Quantum computing. The same principles of entanglement and superposition that might underlie the fabric of space-time are the principles that quantum computers exploit to solve certain problems exponentially faster than classical computers. When Google's Sycamore processor achieved what they called quantum supremacy in 2019, performing a specific calculation in about 200 seconds that would have taken a classical supercomputer roughly 10,000 years. It wasn't just a technological milestone. It was a demonstration that quantum information is physically real, that it can be harnessed, that the universe really does operate according to these strange quantum rules at a fundamental level. and the tools being developed to build and understand quantum computers are, in turn, giving physicists new ways to think about quantum gravity. The quantum error correction codes that protect fragile quantum information in a quantum computer turn out to have deep structural similarities to the way the holographic principle encodes bulk spacetime in boundary degrees of freedom. Ahmed Almheri, Shi Dong, and Daniel Harlow showed in 2015 that the ADS/CFT correspondence can be understood as a quantum error correcting code, that the reason bulk spacetime is robust, the reason a little bit of perturbation on the boundary doesn't destroy the whole interior geometry, is essentially the same reason quantum error correction protects information in a quantum computer. The universe, in some sense, is error corrected. That's a strange and beautiful thought to sit with. The reliability of space, the fact that the geometry around you doesn't randomly glitch or dissolve, it might be because the underlying quantum information is encoded redundantly, spread across many degrees of freedom in a way that protects it from local disturbances. The same principle that will one day let quantum computers operate reliably might be the principle that lets spacetime exist at all. But we should be honest about the limits of what we know, because intellectual honesty is part of the beauty of this whole enterprise. Almost everything I've just described, ER equals EPR, emergent spacetime, it from qubit, works within the framework of ADS/CFT. And as we discussed when we were talking about de Sitter space and the cosmological constant, our universe is not an anti-de Sitter universe. Our universe has a positive cosmological constant. It's expanding, accelerating, and the boundary structure is completely different. So the question that haunts the field, the question that keeps people up at night, and I mean that literally, there are physicists losing sleep over this, is whether these beautiful ideas about emergent spacetime survive the transition from the mathematical playground of ADS space to the real universe we actually live in. There are hints that they do. There's active work on what's called DS/CFT, a hypothetical duality for de Sitter space, though it's much less well understood. Researchers like Eva Silverstein at Stanford and Dionysios Aninos and others have been chipping away at this problem, trying to extend the holographic framework to cosmological spacetimes. And some of the recent results on the page curve and quantum extremal surfaces seem to rely on structures that might be more general than ADS/CFT specifically. But nobody has a clean, complete answer yet. This is the frontier. This is where the map has blank spaces and the notation says, "Here be dragons." And there's another deep puzzle lurking here, one that connects all the way back to the very beginning of our story, to the first fraction of a second after the Big Bang. Because if spacetime is emergent, if it arises from entanglement, then what happened at the Big Bang? Was that the moment when entanglement first arose? Was that the moment when the first quantum correlations flickered into existence, and geometry, space itself, crystallized out of them like frost forming on a cold window? Think about that for a second. If everything we've been exploring tonight is pointing in the right direction, then the Big Bang wasn't just an explosion of matter and energy into some pre-existing emptiness. There was no pre-existing emptiness. There was no before in any spatial or temporal sense that we'd recognize. The Big Bang was the moment when entanglement, quantum correlation between degrees of freedom, became structured enough to give rise to something we'd call a geometry. Space didn't exist and then get filled. Space emerged. It wove itself into being out of quantum information, thread by thread, connection by connection, like a fabric assembling itself from nothing but the relationships between its own fibers. And here's what's genuinely humbling about that idea. We don't have the math to describe it fully. Not yet. We can gesture toward it. We can use the tools of ADS/CFT and tensor networks and quantum error correction to sketch what the early moments might have looked like in some idealized version of the problem. But the actual cosmological case, the real Big Bang, in a universe with a positive cosmological constant, with inflation, with all the messy specifics of the cosmos we actually inhabit, that remains beyond our current reach. And honestly, that's okay. That's more than okay. That's the whole point of doing physics. You don't do physics because you already know the answers. You do physics because the questions are so beautiful that they pull you forward. Let me try to paint the picture as best we can with what we have, though. Imagine rewinding the clock. We've talked about the cosmic microwave background, that snapshot from 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. We've talked about nucleosynthesis, those first few minutes when protons and neutrons fused into helium and lithium. We've talked about the first fraction of a second, when inflation may have stretched a tiny patch of space into the vast cosmos we see today. But now, go further back. Go to the Planck time, that impossibly small interval, about 10 to the minus 43 seconds after whatever the beginning means. At that scale, the temperature and energy density are so extreme that general relativity and quantum mechanics can't both be right simultaneously. The smooth fabric of space-time that Einstein described would be shredded by quantum fluctuations. You can't have a smooth geometry anymore. You can't even talk about distance or duration in the usual sense. This is the regime where we need a theory of quantum gravity, and we don't have a complete one. But here's what the ideas we've been exploring suggest. If space-time is emergent from entanglement, then at the Planck scale, what you have isn't a broken geometry or an infinitely dense point. What you have is a quantum state, a state of some fundamental degrees of freedom, whatever those turn out to be, in which the pattern of entanglement is just barely beginning to organize itself into something that, if you zoom out, if you coarse grain, starts to look like space. It's like, imagine a crowd of people milling around randomly in a field. No structure, no pattern. Then slowly, connections form. People start linking arms with their neighbors. Small clusters appear. The clusters connect to other clusters. And gradually, without anyone giving orders, a vast network emerges. And that network has a shape, a geometry, a dimensionality. That's the metaphor. The people are quantum degrees of freedom. The arms are entanglement. And the shape that emerges is space-time. Now, there's a really provocative idea that's been floating around in the community, and it connects to something we touched on earlier when we talked about inflation. Remember Alan Guth and the idea that the universe underwent this exponential expansion in its first moments? Inflation solves a bunch of problems. It explains why the universe looks so uniform, why it's so flat, why we don't see magnetic monopoles. But inflation has always been a bit mysterious in terms of what drove it. You need some kind of field, the inflaton field, with very specific properties, and the origin of that field has never been entirely clear. Well, some theorists have started wondering whether inflation itself might be connected to the emergence of space-time from entanglement. If the early universe was a state in which entanglement was rapidly spreading, rapidly building new connections between degrees of freedom, then the geometric manifestation of that process might look exactly like exponential expansion. Space would be literally growing because new entanglement links were being created. and each new link would correspond to a new bit of spatial geometry. That's speculative. I want to be clear about that. But it's the kind of speculation that makes you sit up straighter, because it would unify two of the deepest puzzles in cosmology: the origin of inflation and the emergence of spacetime, into a single story. And there's a related question that I find just as fascinating. If spacetime emerges from entanglement, what about time specifically? We've been mostly talking about space, about how spatial geometry can be built from quantum correlations. But time is part of spacetime too, and time has always been the stranger partner in that marriage. In general relativity, time is woven into the fabric of spacetime. It's curved by matter and energy, just like space is, and yet our experience of time feels fundamentally different from our experience of space. We move through time in one direction. We remember the past, but not the future. There's an arrow to it that space doesn't seem to have. Here's the thing. In many of the approaches to quantum gravity, in loop quantum gravity, in certain corners of string theory, and especially in the Wheeler-DeWitt equation, which is one of the oldest attempts to write down a quantum equation for the entire universe, time disappears. Literally. The Wheeler-DeWitt equation, which John Wheeler and Bryce DeWitt formulated in the 1960s, describes the quantum state of the whole universe, and it has no time variable in it. The equation is timeless. The universe, at the most fundamental level, according to this equation, just is. It doesn't evolve. It doesn't change. It sits there as a static quantum state. Now, you might be thinking, well, that's obviously wrong, because things clearly change. I'm lying here, my heart is beating, the earth is spinning, stars are burning. Time is obviously real. And you're right, time is obviously real at our scale. But the deep question is whether time is fundamental or emergent. And a lot of the evidence we've been accumulating tonight points toward emergent. Don Page. Yes, the same Don Page, whose Page curve we talked about in the context of black hole evaporation, proposed an idea back in 1983, along with William Wooters. They suggested that time emerges from entanglement. Specifically, if you have a system that's entangled with a clock, with some other subsystem that you can use as a reference, then even though the overall quantum state is static, the correlations between the system and the clock create the appearance of evolution. The system appears to change in time relative to the clock. Time is not fundamental. Time is what entanglement looks like when you're inside the system, when you're part of the entangled whole, and you can only see your little corner of it. That's a mind-bending idea, and I wouldn't blame you if it washed over you. Let me say it differently. Imagine a photograph, a single, frozen photograph of two dancers mid-spin. The photograph doesn't move. It's static. But the relationship between the two dancers, the angle of their arms, the tilt of their bodies, the way one is leaning into the other, encodes motion. It tells a story of movement, even though the photograph itself is still. In the same way, the quantum state of the universe might be timeless, but the entanglement within it, the correlations between different parts, creates the experience of things happening, of one moment following another, of time flowing. You and I are inside the photograph, and from our perspective, the dance is very much in motion, and this connects to something even broader, something that brings us all the way back to the beginning of tonight's journey. Remember, when we started, we talked about looking up at the night sky and wondering what the stars are made of. We traced the answer through nuclear physics, through the life cycles of stars. through the periodic table being forged in stellar furnaces and supernova explosions. Then we pulled back further and asked about the universe as a whole, its shape, its history, its composition. We discovered that most of it is dark, invisible, made of stuff we can't directly detect. We found that space itself is expanding, and that the expansion is accelerating, driven by something we barely understand. We dove into the deepest structure of reality, into the conflict between general relativity and quantum mechanics, and we found that the resolution might involve space-time itself being woven from quantum entanglement. And now, at the very end, we're arriving at the most fundamental question of all. What is reality made of? And the answer that's emerging, tentatively, incompletely, but with increasing conviction, is information. Quantum information. That's what Wheeler was groping toward with it from bit. That's what the holographic principle is telling us when it says that the information content of a region of space is proportional to its surface area, not its volume. That's what ADS/CFT is demonstrating when it shows that an entire three-dimensional universe can be encoded in a two-dimensional boundary theory. That's what ER equals EPR is whispering when it says that the connections between entangled particles are the same thing as the bridges connecting regions of space-time. Reality, at its deepest level, might not be made of particles or fields or strings or loops. It might be made of relationships, correlations, information. And if that's true, if the universe is, at bottom, a vast quantum information processing system, then there's a strange and beautiful consequence. It means that the laws of physics are, in some sense, the laws of quantum information. The reason gravity exists, the reason space-time has the structure it does, the reason the universe expands the way it does, all of it might ultimately be derivable from the rules governing how quantum information can be stored, processed, and shared. Thermodynamics, gravity, geometry, all emergent from something deeper, something more abstract, something that a quantum computer scientist might recognize as familiar. And here's where I want to leave you with something that I think is genuinely beautiful. Because all of this extraordinary story, from the first hydrogen atoms, to the cosmic web, to black holes, to the holographic principle, to emergent space-time, all of it was figured out by human beings, by people with pencils and chalkboards and later computers. People who stayed up too late arguing about equations, people who made mistakes and had to start over, people who were told their ideas were crazy and turned out to be right, and people who were told their ideas were brilliant and turned out to be wrong. Lemaitre, who was a priest and a physicist, and who saw the expanding universe before almost anyone else. Zwicky, cantankerous and difficult and absolutely correct about dark matter decades before anyone would listen. Vera Rubin, who measured galaxy rotation curves with quiet persistence and changed our understanding of what the universe is made of. Hawking, who couldn't move his body but moved the entire field of theoretical physics. Maldacena, whose single paper launched 1,000 research programs. The LIGO team, who spent 40 years building an instrument sensitive enough to detect a change in distance 1/10,000th the width of a proton. These are human stories. Every equation, every theory, every satellite launched, and every detector built. Behind all of it are people who were curious enough to ask and stubborn enough to keep looking for answers. And the thing is, the story isn't over. Not even close. We still don't know what dark matter is. We still don't know what dark energy is. We don't have a complete theory of quantum gravity. We don't know whether string theory or loop quantum gravity or something nobody has thought of yet is the right path forward. We don't know if the ideas about emergent space-time will survive contact with the real de Sitter universe we live in. We don't know what happened at the very first instant, or whether the very first instant is even a meaningful phrase. The map still has those blank spaces. Here be dragons. But you know what? That's not a reason for frustration. That's a reason for wonder. The fact that we've come this far, that a species of former tree dwellers on a small rocky planet, orbiting an unremarkable star in one of hundreds of billions of galaxies, has figured out this much about the deep structure of reality, that is, by any measure, extraordinary. And the fact that there's still so much left to figure out means the story goes on. Somewhere right now, someone is scribbling an equation on a whiteboard that might be the next breakthrough. Somewhere, a graduate student is staring at data that doesn't quite fit the existing models, and that discrepancy might be the clue that unravels the next mystery. But that's for tomorrow. That's for daylight hours and strong coffee and the restless energy of people who can't stop asking why. Right now, tonight, you've traveled a long way. From the hydrogen in your body, forged in the first minutes after the Big Bang, to the carbon and oxygen in your bones, cooked in the hearts of ancient stars that exploded before our sun was born, to the vast dark scaffolding that shaped the galaxies, to the ripples in space-time from colliding black holes, to the possibility that space and time themselves are woven from something more fundamental. From the quiet, invisible threads of entanglement connecting everything to everything else. You're part of that, literally. The atoms in your body are entangled with the rest of the universe in ways too complex to ever fully trace. You are not separate from the cosmos. You are the cosmos, arranged temporarily into a form that can lie in the dark and wonder about itself. And that right there, might be the most confusing and the most beautiful thing about the universe of all. So let that thought settle. Let it be soft and warm and unhurried. The universe has been here for 13.8 billion years. It's not going anywhere tonight. And neither are you. Just rest now. The stars will keep burning. The galaxies will keep turning. And the deep quantum fabric of reality will keep humming along, whether we understand it fully or not. It's enough for now to know that we're part of it. That's more than enough. That's everything.